It's funny. Have you ever stopped to think about the invisible world that's holding everything together? I mean, everything. The chair you're sitting on, the building you're in, the bridges you cross. There's this hidden architecture of pushes and pulls running the whole show. Well, today, we're going to make that invisible world visible.
Okay, picture this. A traffic light, just hanging over an intersection. It just hangs there, right? It doesn't fall down, it doesn't fly off into space. It seems so ridiculously simple, but have you ever really asked yourself, how? How is it just defying gravity, perfectly still, day in and day out? That's the exact puzzle we're going to solve. You see, that traffic light, which looks like it's doing absolutely nothing, is actually pulling off a constant, perfect balancing act. It's what you might call an everyday miracle of physics, a silent, powerful battle of invisible forces. And to get it, we need to understand the rules of that battle.
So here's the secret. Any object you see that's just sitting still is in a state we call static equilibrium. And this is no accident. It means that every single push and every single pull acting on it has been balanced out perfectly. They've all canceled each other out.
So, to really crack our traffic light puzzle, we first have to learn the language that engineers and physicists use to talk about all these pushes and pulls. It's a language of strength, sure, but also of direction.
At its absolute heart, a force is incredibly simple. It's just a push or a pull on something. Gravity is pulling the traffic light down. The cables, they're pulling it up. Simple enough, right? Well, there's a really crucial detail that we're missing. Think about it like this. If I told you to push a box with, say, 50 pounds of force, what's the very first question you'd ask me? You'd probably say, which way, right? Knowing how hard you're pushing is only half the story. You absolutely have to know which way that push is going.
And this brings us to a super important distinction in physics. Some things, like an object's mass, are what we call scalars. They just have a magnitude, a size, how much. But a force is different. A force is a vector. It has both magnitude, how strong it is, and direction, which way it's pointed. And that direction part is absolutely crucial.
Now, if you look at those cables holding up the traffic light, they're not pulling straight up, are they? They're pulling up and out at an angle. That kind of complicates things. But lucky for us, we have a really cool trick for that. We can take any single angled force and break it into much easier pieces. And this is a total game changer. It turns out any force that's pulling diagonally is secretly doing two jobs at the same time. It's pulling a little bit sideways, and it's pulling a little bit upwards. We call these its horizontal and vertical components, or you'll hear them called the X and Y components.
And we can figure out exactly how much each of those hidden forces is worth with some pretty simple geometry. All you do is imagine a right triangle where the angled force is the long side, the hypotenuse. Then, using some basic trig, good old sine and cosine, we can calculate the other two sides. And boom, those are the exact strengths of our horizontal and vertical forces.
Okay, so we've got our tools. We know that a force is a vector with both strength and direction. And we know how to break down any pesky angled forces into their simple up, down, and left-right parts. Now, we're finally ready for the fundamental rule of balance. The magic word we're looking for is equilibrium. It's this special state where an object, just like our traffic light, stays perfectly still. And it does that because all the forces acting on it add up to, you guessed it, 0.
And this isn't just some neat idea. This is a pillar of physics. It comes straight from the big guy himself, Sir Isaac Newton, and his first law of motion. For anything to stay put, the total combined force, what we call the resultant force, has got to be 0. Period.
And this is the real aha moment. Being at rest doesn't mean there are no forces involved. No. It means that all the forces that are there are locked in a perfect cosmic tug of war. Every little bit of pull downwards is matched by an equal pull upwards. Every bit of pull to the left is matched by an equal pull to the right. It's perfect cancellation.
All right, the moment of truth. We have everything we need. We've got the concepts, we've got the tools. Let's apply this knowledge and finally put the mystery of the hanging traffic light to bed. The very first thing an engineer does in a situation like this is draw something called a free body diagram, or FBD for short. It's like the ultimate tool for seeing the invisible. You just isolate the important part of the problem and draw every single force that's acting on it. And making one is actually super simple. First, you isolate your object. In our case, it's that little knot where all the cables meet. Then you just draw arrows for every single force acting on that knot, and finally, you label them. It makes the whole problem visual and way easier to solve.
So let's do it for our knot. What forces are acting on it? Well, first, you've got the weight of the traffic light itself pulling straight down thanks to gravity. Then you have the tension in cable A, which is pulling up and to the left. And finally, you have the tension in cable B, pulling up and to the right. That's it. 3 forces all meeting at that one single point.
Okay, now we just apply our rule of equilibrium. For that little knot to not move an inch, the total force pulling it down must be perfectly, exactly canceled out by the total force pulling it up.
So how do we find that total upward force when the cables are at an angle? Aha! This is where our secret weapon comes back into play. We break down the angled pulls from cable A and cable B into their vertical parts, their Y components. Each cable contributes a little bit of upward lift, and when you add them together, that combined upward pull is what's fighting against gravity.
And this is what the final balance sheet looks like. In the vertical direction, the upward pull from cable A plus the upward pull from cable B has to add up to be exactly equal to the weight of the light. They're working together to hold it up. And what about the horizontal? Well, for the light to not drift side to side, the leftward pull from cable A has to perfectly cancel out the rightward pull from cable B.
And there you have it. The puzzle is solved. The traffic light doesn't hang there by magic. It hangs there because all those invisible forces pulling it in every direction are in a state of perfect, calculated equilibrium. The combined upward lift from those angled cables exactly equals the downward pull of gravity. So, the next time you see something just sitting there, remember the invisible dance of balanced forces that's making it possible. And I'll leave you with this thought. Now that you can see the unseen forces holding up a simple traffic light, what about the invisible forces that are balancing you right now in your chair?